And thank you everyone else and to CDCB and World Dairy Expo for the opportunity to share what we've done with you. I'll just echo the sentiments of everyone else who stood up here. It's great to finally be in a room with everyone. This is my first opportunity to do so since starting a year and a half ago. So first and foremost, I want to welcome a new hire to our team of scientists, Dr. Sajjad Togiani. He has a PhD in animal breeding and genetics from University of Georgia, and so we look forward to sharing some of his research with you in our following meetings. And on this same topic, we're hiring. We have 2 positions available for animal scientists. These are our support scientists. Every single bit of research I show you today would have been impossible without the work of these people. So we're really excited about welcoming some new talented people to our team. This position closes in about a week here. So the posting can be found on USA Jobs here, as well as on our website. And my email will be up at the end. If you know anyone interested or have questions about it, I would be delighted to answer questions or direct you to the job posting. And so with that, I'm going to jump right into one of 3 research topics we'll be covering today. At this meeting last year, we had just begun investigating this concern about increasing popularity of embryo transfer, but the lack of a parallel reporting of embryo transfer breeding events. So 11% of calves in the US were born last year, 2021, attributable to ET, but only a fraction of the expected breeding events reached us. So that's the red line down there. And initially, we were concerned this was because ET calves were being incorrectly associated with AI breeding events. Fortunately, that doesn't seem to be the case. 97% of these ET calves had no associated breeding event at all. So what do we do about that? How do we handle this unreported ET? And why is this a problem? Well, with embryo transfer, conception's not actually occurring. Pregnancy occurs with the implantation of a high-quality embryo. And so the way the US has handled this in the past is by excluding all known ET donors and recipients. The problem we're dealing with now is they're not known. We don't know who they are. And we don't necessarily want to remove herd years associated with herds who are responsibly using ET. These represent our most elite animals and a larger and larger portion of the dairy cattle population. So in April of this year, CDCB implemented an edit where we've identified herd years reporting over 10% of their calves born by ET, but inconsistent breeding event reporting, less than half of the expected number of ET breeding events given the number of calves born. And so with those records then removed from the analysis, we've recalculated the evaluations for heifer conception rate, cow conception rate, and sire conception rate. So here across the x-axis, we're looking at bull birth year, and across the y, this is just the change in their breeding value before and after the edit. And you can see that the largest effects here, the largest spread across that vertical axis, are in young bulls with high genetic merit. So those would be the red dots here. And I also want to point out that these changes are still, with rare exceptions, happening on the order of 1 to maybe 2 percentage points. And overall, the reduction in records used in this calculation was 1% for every single, for all 3 of these traits. And the correlations with the prior ABVs were over 99%. So at this point, while we have anecdotal reports of big changes for young bulls who have fewer daughter records, the overall effects right now are small. But this isn't a guarantee, especially if ET popularity for cows continues to increase as it has for AI bulls. Over 94% of AI bulls born last year were born by ET. And so there's a critical need to improve this data flow and this reporting. If we're able to acquire more high quality ET records too, considering factors like whether fresh or frozen embryos were used, IVF protocols, we can start to partition the genetic effects between pregnancy rate and conception rate. This work is ongoing. We're currently working on applying this edit to gestation length, and it will probably also be needed to improve the accuracy of DPR as well. Now, in October of last year, the CDCB Board of Directors appointed a task force to look into implementing evaluations for milking speed here in the US. So I'd like to update you on our activities in the last year. Currently, 14 interval participating countries report milking speed, and this phenotyping is almost universally done by subjective scoring, where a trained classifier travels to the farm and works with the farmer to assign scores on a range of 1 to 5 or 1 to 9, ranking them by their speed. And the task force agrees this is unlikely to be practical in the US with larger average herd sizes, and also that it would be advantageous to reduce labor costs and mitigate any potential biases due to the subjective scoring. If milk flow rates are available for these countries, they are used, but this is very rare, and it varies a lot by breed and by country. And so in collaboration with dairy records management systems, we've started to explore what quantitative milking speed data looks like. And so they provided some preliminary data from 9 herds, 7 of which are conventional. And so in this plot here, across the y-axis, we're looking at milking speed in pounds per minute, plotted over day in milk. And so that's across the X. And we can see that milking speed is positively correlated with milk yield, and it's roughly mirroring the milk production curve. Now, some restrictions on days in milk are advisable. Scandinavian countries are using even more restrictive limits than I've shown here. I just sort of arbitrarily chose 10 days in milk and 305 days in milk. And you can see milking speed being quite slower early in lactation prior to 10 days, and this makes intuitive sense with the clearance of colostrum and recovery from inflammation post-parturition, exiting the transition period. And the high variability we see in the cases of extremely persistent lactation are likely due to changes in management. Now, this story becomes a little less clear when we look at robotics herds. So this is the exact same plot we saw before, milking speed on the Y, day in milk on the X, and this is only representing 1 herd. And we can see that milking speed is mirroring this milk production curve, but the data points are a lot less tight. And so for some context, in this herd, they reported up to 6 milkings a day, but not every cow milked 6 times a day, and not the same number of times each day consecutively. Maybe one day she milks 4 times, the next time 3, the next time 2, the next time 5. It's free choice. And her intervals are different, as well as the times of day she might choose to milk. And so it's going to take more data and some sophisticated programming to get a really clear picture of how usable milking speed data is coming off of these machines and what a trait would look like for milking speed in an automated milking system. What are some other conclusions we have? Well, AMS cows tend to milk faster than conventional cows by 1 or 2 pounds per minute. And this suggests that those producers may have been selecting for milking speed on their own already. Milking speed tends to be slightly faster for milkings earlier in the day, suggesting there might be a circadian effect, because milking interval has not been highly correlated with milking speed in conventional herds. That does not necessarily hold for AMS herds, and I'm reluctant to make strong conclusions about what that effect would be without more data. We've also observed that first lactation cows tend to have much slower average milking speed than multiparous cows. This is likely an artifact of culling bias, with hard milkers being removed from the herd, but it could also be related to biological phenomena, like teat sphincters relaxing with age. Now, there are a lot of questions we haven't been able to answer, which leads me to this research agreement under development between AGIL and DRMS. To develop a data set that can help us characterize quantitative milking speed coming off of these systems. And part of the goals here are to assess the impact of what I call system effects, which is a combination of original equipment manufacturer, parlor type, automatic takeoffs, these variable effects that not all farms share, and how much that's impacting these phenotypes. Other considerations are characterizing biological effects, that's breed, parity, and especially udder health. So the interaction between milking speed and clinical mastitis and somatic cell score. And then finally, accounting for system effects and biological effects and determining whether milking speed data coming off of completely different systems can be standardized into a single trait and whether it's suitable for genetic selection. And so this research is just beginning, and we're all very excited, and thank you to many of the task force members here for all of your support and help with this. And so I'll end the milking speed section with a plug for our survey. Many producers in this audience and that I've spoken to so far at Expo are invested in milking speed. They're actively, conventional herds are using milking speed to choose their milking groups. AMS herds are using it to figure out how many robots to buy. We want to hear from you. We want to make sure what we're doing is something that's going to deliver value. So again, please find me at the end. I'm happy to give you a much easier way to access the survey than taking a picture of this link up here. And of course, if you choose to provide your name and email, you'll be entered into a gift card raffle, but that's not required. And your name will be in no way associated with the results of this survey. So this brings me to our last topic, and it's a big one, and it's on getting yields right. And so part of the research here from AGIL I'm presenting is related to a larger project venture between National DHIA and CDCB as well as us to update our projection factors in the way we estimate yields and the way we compare them. So how do we measure yields? What do herds do if they want to know what their yields are? I mean, these are arguably some of the most critical metrics of a success that a farm has. They can be really good indicators of cow health and performance if she's fluctuating a lot day by day. And typically in the US, herds who want to know what their yields are participate in DHI testing. And this involves a technician traveling to the farm and measuring a partial yield. Only one of her yields in a day is sampled. And then from that, her total daily yield is estimated. And so this accounts for factors like whether she's on an AM/PM sampling scheme, what her milking interval is, and other type things like that. Now from these test day yields, her total lactation yields are estimated. And then from that, for fair comparisons among animals, they're standardized to a lactation length of 305 days and the mature equivalent. And so what does that all mean? Well, we know genetic selection changes maturity patterns. And the last time these factors used to standardize these measurements were estimated was in 1994. And at that point, these factors were developed to correct for parity, age within parity, season of freshening, previous days open, geographical region, and all standardized to a 2x milking frequency. And so I want to take you through an example as we're starting to re-estimate these of how they might change and what we might need to consider in looking at that. So there's a lot happening on this graphic. I want to kind of break it down for you. First of all, in these calculations, lactation records are grouped into increments of 5 years. That's what you're seeing in the columns here. So this first column is representing records from 1990 to 95. Then we have 95 to 2000 and all the way down. These are season region corrections. So what you're looking at in those bars on the far right here, the 1, 2, 3, those are our regions. The top being the Northeast, the middle being the Midwest and the South, and then the third one being the West. Now across the x-axis for each of these panels, we have month of freshening, January to June to December. And then across the y, what we're seeing here is the difference in the seasonal effects we observe now compared to when these seasonal effects were estimated in 1994. And all of these numbers here were standardized to those 1994 factors. And so that's this dotted line here at the 1. Right, that's our null value multiplied by anything by 1, it's the same. So if the 1994 factors were perfectly describing season region effects, these lines for milk, fat, and protein would be flat across the 1. And so the reason they're not perfect right now is we have made some other changes to the model, but I don't have time to explain all of that. But what's important is if we look across time here, we do see that seasonal effects are becoming larger. There is a change. And one of the ways we can interpret this is if we look at this upper right panel, we say, we did do this examination by breed. This is just Holstein. A Holstein who calved in June, so that's the peak of that curve there, on the East Coast, that's region 1, between 2015 and 2020, gave an average of 1.4% more milk than was estimated by those 1994 factors. And so this is actually good news. This means that Holsteins now are performing better in hotter temperatures and hotter climates than we thought they would be in 1994. And this is likely also a reflection of us controlling her environment better and better heat stress management and all of those strides in management we've seen in the last 30 years. Now that was an example of how we should revisit standardizing these lactation yields. We also are revisiting methods to estimate daily yields. And so members of our group have come up with this smooth function here where X is representing milking frequency, and it's all standardized to a milking frequency of 2, which is why you've got 2 in the denominator there. And what I mean by smooth function is basically that for any value of X, any possible conceivable milking frequency, we can solve this equation. And so if we pick, let's say, a milking frequency all the way up to 10 times a day, we can plug that in here and plot this function. And again, it's all standardized to 2x. And so we can estimate gains or losses in milk yield based on milking frequency, where if you only milked a cow once a day, you would see a 29% reduction in the amount of milk you'd expect her to give compared to if she was milked twice a day. If you forgot to milk her altogether, you'd see a 100% reduction. If you milked her 3 times a day, you'd see 11% more milk. 4 times a day, 16%, and so on, until we sort of hit a point of diminishing returns. Now, this equation assumes equal milking intervals, which we know is rarely true, and does have an impact on milk production. So we can adjust this equation where we have this term here, W sub I, which is simply the proportion of time in a day she had to make milk. But then we have this other interaction term here, which is the frequency of milking based on this particular interval. And this is really important. And the reason why is mathematically, we can define a given number of milkings in a set 24-hour period. But the cow's biology does not know that. So if we have a 3X cow and we know her interval is 6, 6, 12, but if she's milked again after 6 hours, she might think she's actually a 4X cow with 6, 6, 6, 6 intervals. And that will absolutely be reflected in the amount of milk she gives in her next milking. And so what this term does is it accounts for that. And then we would take this and we would sum that interaction term for all of her milkings in a given 24-hour period. So what does that look like? What does that tell us? This table is showing exactly what you saw in that graph earlier, where we've got this standard comparison of 2x frequency, 3x and 4x, the gains in milk estimated, assuming equal intervals. In a 2x herd, if she's off by 1 hour, we see a 0.2% reduction in milk yield. If she's off by another hour, 1%. If she's significantly imbalanced, we see a 3.6 reduction in milk yield, which might be a sufficient pain point to revisit her milking schedule. If we look at these same trends for 3x and 4x herds, we see the same story. We see that consistently you get more milk from more milkings a day, even with uneven intervals. Although within milking frequency, if she has uneven intervals, she does give less milk than if she was milked evenly. And what's interesting and cool about this algorithm is that we can predict milk gains or losses from an infinite set of intervals in milking frequencies. And this is especially exciting as we see more herds starting to utilize robotics. You'll remember the graph I showed up there of milking speed in the AMS herd, and it was extremely difficult to identify a consistent pattern day by day. And it's because of this high variation that cows have in their milking frequency and intervals, both within days and across days. And so our hope is that this can become a really useful tool for both management insights in the day-to-day running of your farm, but also genetic evaluation. Now, all of these numbers were tested and these methods were developed using simulation data. Dr. Nick Wu at CDCB has done some preliminary testing with a small data set and has found that this method does fit the data very well. But to have any sort of confidence and true confidence and validation in these methods and in these factors that we want to put out to the industry, we need to have comprehensive data. And so that brings me to this field study that's being spearheaded by National DHIA at CDCB, which involves enrolling herds across the United States that capture dairy systems demographics. So these are the most common breeds, numbers of lactations, as well as housing and milking frequency management systems. And so the idea is that for these herds, a subset of cows will be chosen, and then in their first 120 days in milk, they'll be sampled weekly. And then for the rest of their lactation, sampled monthly according to the regular DHI schedule with the rest of their herd. And the justification for this is that we want as much resolution as is realistic in early lactation, because this is when key economic decisions are being made. Farmers are choosing who to cull, who to breed to who to sell. And so we want to fine-tune these predictions of total lactation yields as early as possible. And so we're really excited about this work. We think it'll have immediate benefit to producers as well as long-term genetic impacts. Another thing I didn't quite get into too much just due to time restrictions is those seasonal factors you looked at were different from how they've been calculated in the past. They were adjusted to 36 months as opposed to mature equivalent, just as the traditional PTAs have been since about 2007 when we switched to the all-breed model. And the reason for this is that it allows fairer comparisons across breeds, but also that's more representative of the cows we're actually milking. Several people have brought up the point today that we need to make these cows last. Very few of them reach mature equivalent. So average age, 36 months, might be a more interpretable way to view these correction factors, just as the traditional PTAs are. And so with that, I want to keep us on schedule and not dig into Joao's time too much, but I'd be delighted to take more questions afterwards as well. Thank you.